The data center building boom is big. How big is it? Well, according to a story this morning in the Washington Post, big tech companies are pouring so much money into data centers, they may literally be propping up the entire American economy.
Now, these drab-looking buildings are popping up in cornfields and industrial parks across the country. Pennsylvania officials clearly want them. Within the last couple of months, state leaders announced over $100 billion in data center-related investment.
And that money is tantalizing for a post-industrial state like Pennsylvania. It's also risky. Data centers require tons of energy, enough to drive up your electricity bill, and there's concern this building frenzy will come at a steep environmental cost.
So how enthused or worried should we be? To help us navigate that question, we've invited Cade Metz, technology correspondent with the New York Times. Cade, welcome and thanks for being here.
Glad to be here. Thank you.
We also have in studio Benjamin Lee, professor of electrical and systems engineering at the University of Pennsylvania. Ben, welcome.
Great to be here. Thanks so much.
Cade, for folks who've never seen a data center, I want you to help paint a picture. What are we talking about here? What's inside these humongous buildings?
Well, if you've used the internet, which we all have, you've used a data center, right? When you make a search on Google, when you visit Amazon to buy something, you're calling a computer across the internet that is housed in a data center operated by one of these giant tech companies. And these data centers, built by companies like Amazon and Google, have been around for decades. These companies are built on these giant football stadium-sized computing centers. But what we're seeing now is an increase in the amount of computing power, the amount of electricity that are going into these things. These are pretty drab buildings. If you've seen one data center, you've seen them all. It's rows and rows of computers.
What's so fascinating about all of this to me, Ben, is that these data centers have been around for a while. And over that period of time, we're becoming more and more reliant on our computers. But overall, it seems like energy consumption in America was actually pretty stable. So whatever these data centers were doing, they weren't drawing up enough power to influence the big picture of how much electricity our country needs to run. And then something changed. What changed?
Right. So the focus on artificial intelligence, first with the advent of training these massive models that can respond to queries and natural language prompts, that was a big sea change. Now we needed these systems that could process massive amounts of data and also churn for weeks or months on end in coordination. You might have 100,000 of these chips in a coordinated fashion, learning what the next language model might need to do or might need to respond to. So that was a huge change, and that changed what goes into the data center. We went from central processing units, the types that we have in our laptops.
That's the type of chip.
The chips.
Yeah.
Right. And so these chips have been sitting in our laptops and our tablets and our phones for years, for decades. But now we're talking about GPUs, these really capable chips that are great at the maths required for AI, and they draw a lot more power. Not only when we use them to train these really advanced models, but also when we start using these advanced models, when we start asking these models to do things for us, we're turning to these same chips that draw a lot of power. So collectively, the training of these models, but also the use of these models are driving those power costs up by order of magnitude, 10x, maybe even 100x.
What is the argument, Cade, that the big tech companies are making as for why we need to do all of this so quickly?
Well, the argument is wide, and the ideas are myriad. But basically, they're saying that this is going to accelerate the economy. It's going to accelerate the work that so much of us do, beginning with computer programmers. It's going to allow them to write computer code and build applications quicker. It's going to allow people to, in a business setting, write official documents, legal documents, et cetera, at a faster rate. And if you accelerate people's work, then in the end, you make more money. They're even making even larger claims about these models eventually curing cancer, and helping to accelerate drug discovery. Um, that sort of thing is still very much in the future. And what we have today is a system, something like ChatGPT and the technology behind it that can accelerate programming. Um, it can help you write documents, but it's yet to be seen how much that will really change the economy. And the other thing to remember, and we'll get into this, is just how expensive
Mm.
is just to serve up these applications. And it's unclear if they can get the price down to make this a really viable thing for businesses and individuals. But they're promising a lot that's still in the future. In the meantime, they're all in a race, right? It's like FOMO. None of
Well,
these.
that's what I was going to ask
Yeah,
about,
yeah.
Cade. They must be also considering the price of not doing it, the opportunity cost. And I don't know if, Ben, you have some takes on that.
Right, and just to build on that, the fear of missing out is pervasive in big tech right now.
Yeah.
We see these transitions happen periodically in tech where the dominant player like Microsoft goes through this phase where they have to reinvent themselves, and now they're coming back out with their partnership with OpenAI and other models. So this constant reinvention, this disruptive reinvention is driving a lot of this capital investment in capital infrastructure. So that's within the United States. And then, of course, geopolitically, we see this discussion about the fear of missing out, the fear of losing dominance in energy and in AI and in technology. And that's driving a lot of the discussions both within the United States and abroad. And I think the potential benefits are out into the future. This moment reminds me of when I started studying computing at the dawn of the internet, right? So we saw this massive investment in the internet, in networking infrastructure and so on. And we didn't really see the immediate benefits. People were creating these random web pages for pets.com or whatever. But nowadays, we realize that the internet has fundamentally changed the way we live and the way we work. But it took 10, 15 years for the advent of the internet to Google and Meta.
So that's the
and these
time
other
horizon
services.
these guys are thinking along potentially.
Right. So building out the platforms, building out the infrastructure so that you're ready for those what we call killer apps, those dominant applications, or those dominant use cases. The reason why there is, I think, a lot of skepticism, rightly, from some of these people in the audience is that we don't know what those outcomes will be. We're still very much in the exploratory phase.
Are we sort of in an archaic like I'm thinking now right now, Ben, about how we today would view something like the ENIAC, like a computer takes up a whole building. That's crazy. Someday down the road, will the technology get better so that the footprint of these is smaller and the energy cost is smaller? Maybe that's building them under the ground. Maybe that's not a CPU, a GPU, but an XPU, some other type of chip. I mean, are we on that progression, or is this kind of going to be the state of play for a while?
That's a great question, and unfortunately, I think we may be in this state of play for a while. Not to get too technical, ever since the 60s, computing has benefited from Moore's law, right? The technology scaling, transistors getting smaller, using less power, so we could build chips that did more with less power. For deeply technical reasons, Moore's law, that shrinking of the transistor and also the power reductions of the power that they're using, that's not playing out anymore.
It's stalling out.
It's stalling out.
Oh, gosh.
It's stalling out. So as a result, you can double the performance of your system, double the performance of your chip, but you may end up building bigger chips, building bigger systems. So this is really incredibly unfortunate because we had this really sharp scaling trajectory for the underlying technology, but that stopped. And we're seeing exponential demand for computing just as
We
that
need
trend
lots
has
of computing power, but we have not managed to make these things smaller and smaller and more efficient as we were in prior decades.
Exactly.
These data centers are changing the way we use energy, the way we use water. And, can you sort of talk about in the sense that as we try to understand how these centers work, how do they impact the environment and bring it all in so we can kind of understand what are the tentacles of impacts that surround these centers?
Yeah, I think the first thing you have to realize is that this technology is fundamentally different than anything we've used in the past. So, if you used a Google search engine, for instance, in the past, and you did a query, you would hit one one machine across the internet, right? One chip. You're asking for some information and it delivers it to you. These chatbots are built in a different way. You're not grabbing a single piece of information. You're grabbing this system that has been trained on literally the entire internet. So you take all the text on the internet and you feed it into this system, and it spends months analyzing all that text and identifying patterns in all that text, and it learns the skills that you now see from a chatbot. But what that means is that all that information is analyzed by hundreds, thousands, now even more chips. That's the way it's built. And then when you have to deliver the system, you also have to query all this information via all sorts of chips. So each time you do you key something into ChatGPT, it's hitting all sorts of chips across these data centers.
And so, what does that mean for power? Is that how why it's basically a power drain or a power suck?
That's exactly right. So rather than just hitting one chip, you're hitting thousands of chips, and that requires electrical power. So every time you type something into ChatGPT today, it's so expensive that these companies are losing lots of money, even likely when you're paying for an advanced version of something like ChatGPT. Those companies are probably taking a hit because it's so expensive because of the power.
Yeah.
Now, one way to think about this, and this ties into the environmental question, is that so much power is required that these things get far hotter than the machines of the past. So in the past, the systems on those long rows of computers I talked about within a data center, they would get hot, and basically what you would do is you would pump cool air beside these systems, and you would cool it down. And as time went on, you would find ways of cooling them down through water. You could run the hot air beside a water pipe, basically, and cool it down. Now, these chips that are doing the AI work are getting so hot, they're using so much electrical power that you have to run the water all the way to the system, all the way to the rack, as they say. There are racks of computers. You run the water, the cool water, all the way there. And in some cases, I've seen this, all the way to the chip itself. So the chip itself is getting so hot, the water has to go all the way there. And many of these data centers are using far more water in that way. And that's why you might need water from the environment.